particles come into existence. Okay, so this is with timeline, and we are now here 2024, and I'll be talking about, say, 1900s time. So how the various models come into existence. Let's talk about some history. Now, you all don't like to know history most of the time, but I'll be talking about not just when the model was developed, but also what was the basic philosophy. So in a way, you can get a basic conceptual idea behind the actual physical working of each model. Fine. So let's start. So the first thing was, you see, we already know that nuclear forces are complicated, and so it was clear that their net effect is to hold the nucleus together. So this nuclear force was first represented by a very simple model, which is just an overall attractive potential, which is parameterized by depth and range. Remember the deuteron problem? This is very much similar to that, similar to our deuteron problem. Okay, so basically this is your deuteron problem. So basically this matter, we call it extreme single particle model. This is your extreme single particle model. Now, however, we soon found that many of the nuclear properties using this model did not agree with your experiment. And so, around your 1936 came the later model, next model, which was the compound nucleus model of Niels Bohr. So, compound nucleus model by Niels Bohr. Now, this model took full account of the observed strong interaction between the nucleons. So basically, unlike this previous model, here there was very much strong interaction between the nucleons inside the nucleus. According to this model, basically a nuclear reaction, so remember this is a model for nuclear reaction. So according to which a nuclear reaction takes place in two distinct steps. I'm not writing each and everything, I'm just telling you. Step 1 and then your step 2, two-step process. Two-step process. In the first step, basically what happens is that the incoming particles are captured by the nucleons, by the nucleus, thereby forming a compound nucleus, and this is followed by a relatively long period over which the energy brought into by the incident particle is shared and reshared among the various nucleons by interactions. Okay, this is all happening inside the compound nucleus. So the compound nucleus absorbs the incident projectile, and then redistribution happens, energy, momentum and all that. So this is the first step, formation of compound nucleus. Yes, formation of compound nucleus. And now the second step is by statistical fluctuation through energy, which is concerned on a nucleon or a group of nucleons near the surface, and then it enables it to escape. So basically, after the formation, some statistical fluctuation due to which one nucleon or a group of nucleons escape this compound nucleus near the surface. So this is the escape of ejectile and formation of your residue nucleus. Now this model was very good and it was successful for many years, but you see in around 1940s or so, yes, in 1940s, just a second, yes, around 1940s or so, what happens is that it was observed that many properties of the nucleus show marked changes whenever the number of neutrons or protons in them correspond to special set of numbers, and these are basically the discovery, you can say, of magic numbers. And this was very important. This observation basically pointed to the existence of some sort of cell structure. So this pointed to existence of shell structure in nuclei. And this was not the first time that we have observed such a situation. Previously, you all know that in the case of atomic physics as well, we have observed this. However, the situation here is very different. In the case of atomic physics, we have the electromagnetic force which was due to the nucleus. But now, this time, where is the force coming on? There is no point, you can say. Previously, during the case of atomic physics, we considered the atomic nucleus as a point charge, and there the electrons were revolving around. But here, right now, we are talking about the nucleus itself and nucleons moving around. So where is the force coming? What is the basic origin of this force? Okay. Now, several attempts were made to find a model that could predict these magic numbers. So basically now our attention was to predict, basically development of a model. A lot of people were working on it so that these magic numbers could be predicted. However, successfully, Mayer, Haxel, Jensen and Seuss in 1949. Okay, Mayer, Haxel, Jensen and Seuss, they postulated a strong coupling between the spin and orbital angular momentum of each nucleon in addition to the central potential. Remember, these workers, they did this independently. Okay, yes, so basically here we are talking about, where is this? Yeah, so basically now as a result of their investigation, we are talking about the addition of harmonic oscillator, and this is some coupling constant L dot S. So this is our potential, the nuclear potential. Now this combination of potential, basically this gave rise to energy levels for nucleons which were such that they were now filled by nucleons separately for neutrons and protons according to the requirements of Pauli principle, and this produced closed shell at the magic numbers. So this was basically developed to reproduce the magic numbers. Now the idea is very simple. You see, if you have a harmonic oscillator, you know harmonic oscillator levels are equidistant, so you will never get magic numbers in this way. you cannot explain extra stability. But if you introduce harmonic oscillator plus L dot S, then there is some bunching. You see, this is bunching effect. So some levels are close together like here, then there is a gap, and this gap basically means your magic numbers. Say for example 2, 8, 20. So 28. So say levels up to this are filled by 20, and then okay, so basically what will happen? Tell me students. If the nucleons are filled up to this level, 20 nucleons are filled up, then the 21st nucleon, I am talking independently about neutrons and protons. So let me just right now talk about neutrons. The 21st neutron will have to be placed at a very high energy. See the gap? And so this means the 20th nucleon will be very much stable. The structure of this nucleus with 20 neutrons will be stable compared to the structure of the 21st neutron. A large energy will be required to put the 21st neutron. Okay, so this means high separation energies. And this is how the magic numbers were reproduced by introduction of bunching of levels. So this is obtained. So this bunching of levels is the key. So you see, this choice of harmonic oscillator caused bunching of levels. And now we can reproduce this magic number. And this is our, what is the name of this model? This is our shell model. Okay. So basically we talked about a very simple extreme single particle model, next compound nucleus model, and now shell model. Now you see the success of this compound nuclear model for reaction and shell model for structure, it caused a great interest in physicists. However, if you look closely at the assumptions involved in the two models, then you will feel a puzzling situation. How? You see, in compound nucleus model over here, what is the basic requirement? Basically the compound nucleus model, see this one, this requires the nucleons and the nucleus to interact strongly, and so this may be termed as a strong interaction model. However, what happens in the case of shell model? You see, in the case of shell model, what we require is that all nucleons inside the nucleus interact only weakly and move in such a way that they describe one or more complete orbit before undergoing a collision with other nucleons. Now you see, only under these circumstances the orbit picture of motion of the nucleons inside the nucleus could be meaningful. But the question is, how with so many nucleons confined to move in such a small volume, okay, and with such strong interaction between them? See, we know that from the binding energy, what's the value of binding energy per nucleon? Of the order of MeV, right? So the interaction is very strong. So the question is, how is this happening? So that, what I mean to say, how are the nucleons moving around in complete orbits when the when the nuclear force is so strong and there is no collision between them? Now the answer to this puzzling issue came in 1950s. Okay, the answer came in 1950s by Bruckner and its collaborators, 1950s to 60s basically, and they developed models for obtaining approximate solutions to the many body problem. Models for approx solutions of many body problem, okay, containing the very large number of nucleons. Now this you will study in advanced nuclear physics course. I am not going to talk a lot about them, but this is important that this puzzle was explained. Now the explanation basically is that starting from your two nucleon forces, these people, Bruckner and their collaborators, they arrived at solutions which supported orbit-like picture of motion of nucleons in the nucleus. So they correlated this picture. So now, starting from the nuclear force, they arrived at the orbit-like picture. Their solutions did that. And the explanation of the success of this model, which is basically termed as individual particle model. So, in short, it is known as IPM, individual particle model. Basically relies on Pauli's exclusion principle. Previously I talked about, remember when I was talking about this compound nucleus, this is basically a strong interaction model, or SIM in short, strong interaction model. Okay, let us see how the problem of collisions was solved. Let us just have a qualitative discussion. You see, each nucleon orbit, just a second, yeah. So, yes, each nucleon orbit, fine, it corresponds to a set of quantum numbers, and every nucleon being a fermion, so they will follow the exclusion principle. That means no two nucleons of one type, either proton or neutron, can have all their quantum numbers same in the allowed states of motion. So this means that in this way Pauli's exclusion principle forbids most of the collisions that would otherwise take place within the nucleus. Why? Because they would lead to states for nucleons that are already occupied. But when a nucleon or a group of nucleons enter the nucleus from outside, it has much higher energy. Say like this. Say the situation is somewhat like this. So this is the potential. Now the lowers are field levels. So the thing is that, let us talk about this particular nucleon. Say for example this one. Yes, this nucleon. Now if I say that this will undergo collision with this nearby nucleon, then where will it go? Because Pauli's exclusion principle forbids same two nucleons to have the same quantum number. Now, so they cannot, even if, so where will they go after collision? Because you see, there are no unfilled states to go after the collision. It's not right, you understand? So because of this situation that all the states are filled levels, so there can be no collision among these nucleons. However, the new ones which can enter from the projectile during a nuclear reaction, when they enter, they have got much higher energy, right? So as this nucleon or a group of nucleons, they are coming at much higher energy, they can now interact with them, and as a result there can be collision and this nucleon can get excited and go up. So understand? So this means that such nucleons will go to higher energy states which are usually not already occupied, and in this way the interaction takes place strongly. Now, the absorption of nucleons in the nucleus was included in the simple models by allowing the potential to become complex. So, previously we have talked about extreme single particle compound nuclear shell model. Now this individual particle model, IPM, this is basically a microscopic model. Okay, and now we are coming close to the optical model. This is again a model for nuclear reaction, optical model. So what happens here, now we have a complex potential. You see, a complex potential basically, so in this optical model we have complex potential, and this complex potential, let me give you an example. So the complex wave vector is basically given by this 2n v minus k, sorry, E minus v by h cross, right? Now this is equal to say k1 plus ik2. Previously we were always talking about the real one. Now we have got this complex nature, so imaginary part is there, and this imaginary parts take care of the absorption. You can see my optical model lecture regarding this. Okay, so how many models we have considered? Basically, the first one was extreme single particle model, the second one was compound nuclear model, the third one was shell model, and this is the individual particle model as a result of Bruckner and its collaborations. And we have now got the fifth model, which is the optical model, which takes into account the absorption effect. You can look into my optical model lecture to get more idea. Absorption effects, that means the nucleus, the elastic scattering, as well as this K1. Now this wave number becomes complex. The real part takes care of the elastic scattering part, and the K2 component now takes care for the inelastic scattering plus nuclear reactions part, and this K1 takes care for the elastic scattering part. Okay, and if you ask me, I have already talked about how this individual particle model takes care of the collisions. So basically what we have is that each nucleon orbit basically corresponds to certain set of quantum numbers, and nucleons, which are basically fermions, so they follow exclusion principle. This means that they cannot have all the quantum numbers same in any allowed states of motion, and in this way the Pauli's exclusion principle, it basically forbids most of the collisions that would otherwise take place within the nucleus. So the fermionic nature helps us in this way. Why? Because this way the nucleons, you see here, they are already filled. So where will they go after the collisions? However, the states which are higher in energy, say for example near the surface, what happens when a projectile comes? Now let us consider projectile to be a single nucleon or a group of nucleons. So during a nuclear reaction, when a projectile interacts with a target, so projectile is interacting with a target, so this is my projectile and this one is my target. So what happens? These nuclei basically, they have much higher energy, so they go to higher energy states which are not usually occupied, and then there can be interaction with the low lying states, and as a result of the interaction there are filled states to go to. So in this way the interaction between projectile and the target nuclei takes place. Understand? And so we have talked about 5 nuclear models. Fine. So now, important point to note is that in all these situations, all these 5 cases till now, what we have done is, all these cases we have assumed that the nucleus is in spherical shape. Right. Since the overall attractive potential was taken to be central. But during this period, sometimes some data was observed, lots of data. In a particular mass region, you can say, we have observed, and what was observed is that, so we observed data which showed that the electric quadrupole moments and strengths of E2 transitions in many nuclei, what did they show? They showed that the nuclei are not spherical but deformed nuclei. How do I know that? You see, what we can do, say for example the shell model. From the shell model we can try to explain the quadrupole moment, and it was observed that the shell model has limited applicability. There are so many nuclei out there whose quadrupole moment is very much larger compared to what the shell model can predict, and this basically indicates that the nuclear potential is not spherical at all in those nuclei but are in fact deformed. Okay. Another thing which was observed is that for these nuclei where the electric quadrupole moments were very high, in this nuclei basically we observed a different mode of excitation. We observed collective excitation modes, vibrational, rotational and all that, and the nature of these excitations was very much different from the single particle excitation spectrum, which can be explained very nicely by the shell model. Now let me give you an example for this data. Okay, let me give you an example of this data. You see, let us consider the closed shell nuclei in which neutrons and protons are both magic. Say for example 16 oxygen, 40 calcium and your 208 lead. Now these are all spherical, fine, which is expected from the high symmetry of closed shells. But as the number of nucleons outside the closed shell increases, the deformation in nuclei increases. Basically what is happening is, I will talk about this little bit later, maybe it will be for the good. So what I want to say is that basically what was experimentally observed is that the quadrupole moment was always positive before the shell was filled and negative immediately after. This behavior of quadrupole moment calculated on the basis of single particle picture from the orbits only of the nucleons outside the closed shell was actually inadequate, which I told you. Okay, so the thing is that these nuclei, closed shell, magic number nuclei, they are spherical. But interestingly, let me tell you, if you consider the 16 oxygen nucleus, in ground state this is spherical, but if you go to a very high excited state, say 5 MeV above, then you will observe collective excitations as well. So how do you expect? How do you explain this thing? Students, you have learnt in your school, in your college, in your books that these are magic number nuclei. They always show single particle behavior, right? However, if you, that is for the ground state, very close to it. If you go to excited state in the shell model picture, what happens is that they are filled. Okay, now if you go to very high states, what happens is that all the nuclei for excited state spectroscopy, basically the nuclear excitations are involved. That means these nucleons which are filled previously, they will be rising to the high line states, and this is the result of collectivity. This means that now their behavior is very much different from the previous filled situation, and because of this excitation in levels, high lying orbitals, even this closed shell nuclei will start behaving collectively. So they will show collective excitations. Now, how did people when did people first realize this? Well, you see, in 1950s, basically 1950, it was Rainwater who suggested that the extra nucleons can polarize the core, considering it to be a liquid drop so that it becomes spheroidal. So the idea is like this. Let me show you. The idea is like this. We have got a spherical nucleus, and so if we have got spherical nucleus, when all the levels are filled up to this part, say this is a closed shell, okay, closed, filled. Now when the next nucleons are going to the high lying states, say for example here, it is not completely filled, there is half filled, you can say, not completely filled. So these nucleons can sometimes, so they are outside this core, this spherical core, and they have, in fact, they will basically, as a result of them, entire potential will now become non-spherical. You see the matter distribution itself, the thing is spherical when it is fully filled. Now this is not fully filled, this is less than half filled, and as a result you can see the matter distribution can sometimes become non-spherical when all of the nuclei are in one way. Now you can say that such situations can then of course can happen, and there can be also situations like this where the nuclei will be uniformly but again there can be situations like this as well. So as a result there can be vibrations. So sometimes the matter distribution is like this, sometimes the matter distribution is like this. So if this is so, then the entire matter distribution is basically vibrating, you can say, from this situation to this situation. So this is the origin of vibrational excitation, you can say. The entire matter distribution can change somewhat. So basic idea is this thing, what I am showing you here, these nucleons, they are basically sort of polarizing the core in this way, and the entire your potential, the nucleus itself now doesn't remain spherical but spheroidal, and thus the shape of the nucleus results from its own stabilizing effect, the surface tension of the liquid drop. Now you can think of a liquid drop like this. So this is basically your liquid drop model. Okay, so this is your, say, sixth model. In this way you can say. And this is now the beginning of collective models. Till now we were talking about spherical nuclei. Now from the experimental data it was observed that some nuclei have very large quadrupole moment, and so we need deformation, and this was the origin. So the idea is that the extra nucleons can polarize the core, considering it to be a liquid drop, just like liquid drop vibrates. So there will be vibration. And so the shape of the nucleus results from its own stabilizing forces. And the surface tension of the liquid drop basically tending to make it spherical, and the forces from the extra core nucleons which tend to deform it. So basically you see there are two forces. One is the surface tension which tries to make it spherical, and then there is force due to these polarized nucleons which will try to deform it, and there is basically competition between them. As a result, there will be sort of vibration. Now in fact rainwater showed that this picture gives quadrupole moment, which was quite similar to the experimental values, and in fact it also accounted for their variation with shell structure. And so with this idea by rainwater, you see, this was the origin. So with the rainwater's suggestion, then nuclear deformation was further developed by Bohr and Mottelson. This is very important. And this was the year of 1950s, and a lot of other peoples were involved as well, but they are the principal characters, principal players in this nuclear deformation development game. Now in the earlier studies, these collaborators, this Bohr, Mottelson and the collaborators, they considered the nuclear core as a charged deformed drop. So now say considered as a charged deformed drop of nuclear liquid interacting with a few nucleons outside the core. Nuclear liquid interacting with a few nucleons outside the core. Now they describe the motion of the core by a few dynamical variables, which are basically the collective coordinates. While the extra core nucleons were treated individually. So the basic idea was that now core was described by these collective coordinates, and the extra core nucleons they were treated individually. Now this was the earlier studies. So this was your earlier studies by Bohr and Mottelson's group. Now in later studies, what they did was, they considered all nucleons in the nucleus. Now they are considering all nucleons in nucleus as moving in non-spherical potential, and this represents the long-range correlation, which represents the long-range correlations between nucleons. Now, from these studies, these later studies, it was inferred that the nuclear deformations can be of two types, which may be termed static and dynamic, or in simple terms, hard nuclei and soft nuclei. So hard nuclei and soft nuclei. Okay, so what are these? Basically, now the hard nuclei were those that preserved their shape. So they preserved their shape. Now if such nuclei are deformed, they can be set into rotatory motion. So after deformation, they can be set to rotational motion. See, just like a rotating rugby football. Now one can easily calculate the energy levels of such system by applying quantum mechanics. And what? You can do this yourself as well. Yes, it is very simple, not very hard. So basically the energy level here, this is equal to H cross into L plus 1 by 2I. I is the moment, I is here, H cross twice L by twice I. This I here is the moment of inertia, okay, of the rotating nucleus, and L is the spin. Okay, now so basically here we observe rotational bands. Basically they are particularly observed in, say, rare earths. Okay, now next let us talk about the soft nuclei. Here oscillations or vibrations, basically oscillations or vibrations can be easily induced because of this deformation, like the wobbling of a jelly. So this one is like wobbling of a jelly, and this was like a rotating rugby ball, football, and this is like the example I am giving, wobbling of a jelly. Okay, now such vibrational states, so basically it predicts vibrational states which were actually seen experimentally in some nuclei, and it is found that the vibrational spectra are not as well marked as the rotational spectra of the hard nuclei. This is because, you see, the vibrational motion is easily coupled to other types of motion, and as a result we get to see complicated spectrum. So we have observed hard nuclei and soft nuclei. Now the rotational and vibrational models of nuclei that we have just described are both known as basically collective models. So this is the collective model. Now more specifically I should say geometric collective model. Geometric collective model. Okay, there is yet another collective model which is algebraic collective model. I'll talk about it later on. Now, so basically in these collective models, here nuclei show collective or bulk behavior, bulk motion, unlike the single particle behavior like that of shell model. So you can easily picture the nucleons to be still moving rapidly along the independent shell model orbits, but on longer time scale the orbits change in such a coordinate way that there is a resultant bulk motion of the nucleons, which may correspond to rotational or vibrational motion of the nucleus as a whole. Now, in the later model, the shell model potential is assumed to be spherical. No, not spherical, but non-spherical. See, so now I am till now I have talked about collective model, and now I am basically moving towards a unification. So next step. So just a second. Yes. So this is rainwater's theory number. So number 5. Then liquid drop model number 6. Sort of is various application by rainwater, and then this was the geometric collective model. So number 7. And now I am talking about the unified model number 8, or the distorted shell model. Shell model, sometimes also known as unified model. Okay, so this is my number 8. So here I am basically unifying both the shell model and the geometric collective model. So I am considering now a non-spherical potential. See, let me again. So what I am doing is, now we are trying to picture the nucleons to be still moving rapidly along the independent shell model orbits, but on a longer time scale the orbits change in such a coordinated way that there is a resultant bulk motion of the nucleons, which may correspond to rotational or vibrational motion of the nucleus as a whole. So you see, in this case now, the shell model potential is basically assumed to be non-spherical, and the energy levels of the nucleons in this non-spherical potential are calculated, and the distortion is taken to exist, which gives minimum energy. This is the concept of your what? Unified model. Understand? So let me again say what I've just told. So basically, previously in the collective model we have considered first a core part which was collective, and then individual outside core nucleons to behave independently. First version. Next version was we considered the entire core nucleons to behave collectively, and various models were developed in this geometric collective model. They are the two versions of the geometric collective model. And now we also have the shell model, right, where the potential is spherical or so. Now what we are doing right now is the following. Now we are incorporating both these effects in this unified model or your Nielsen model. This is your also Nielsen model. Unified model, Nielsen model. So now what I am doing is, I am saying that because of this entire collectivity, the core itself is now deformed, and now I am talking about nucleons outside the deformed core. So I will be talking about nucleons outside the deformed core. So again, now my shell model description remains, where because of the effect of this collectivity I have deformed the core as well. So this is your Nielsen model. Now there is yet another model which is of importance. This is basically known as your nuclear cluster model. Okay, so this is your model number 9, you can say. Now what happens here is this. Basically, in this particular model, the nucleons in the nucleus are considered to group together in energetically favored cluster. So here basically the nucleons inside nucleus are considered to be grouped together in energetically favored clusters. Let me give you an example. Say for example the 6 lithium nucleus. Now we may consider it to be a tightly bound alpha and a deuteron moving around one another. Okay, so this is an example of cluster nucleus, cluster model.